I don't know if I should start or wait for someone to give a signal. I'll be warm because I will be moving a lot, but yeah. So maybe if somebody is cold, you can go to Blackboard and do some exercises to help me. Great. So now, so for the rest of the week, now you're left with me. So sorry, it's not gonna be so. There is an echo. Maybe I can just move it further away. Can you hear me? No. I know. Maybe I know what's happening. Have to maybe make Zoom quiet. But no, but it shouldn't be. Okay. Oh, okay. I think now it's good. Perfect. So it's gonna be probably less deep, more down to earth for the rest of this week. But yeah, we'll see. In the first two lectures I was walking you through some examples of EFT to show you the philosophy, and I think that presentation was pretty standard. So I mean, if you go to YouTube or to some other lectures, yeah, you will see this kind of introduction, yeah, in a bit reshuffled, yeah, but essentials are the same. On the other hand, yeah, the next three lectures will be a little bit more original. I don't know if they will be interesting, but certainly I think it will be a bit harder to find it in this particular form. Yeah, this kind of presentations. Yeah, I don't think this exists. And today I want to talk about non-relativistic EFTs. Yeah, so that's the topic that is probably less familiar to most of you, yeah, because you are high energy physicists and you don't care what's happening at low energies. But yeah, it is important, yeah, because a lot of it's easy to forget, but a lot of the things happen, yeah, in the non-relativistic regime actually. So, and including a lot of precision experiments, yeah. Like one example would be that I will talk about is beta decay nuclear physics, yeah, but there is a lot of other examples, yeah. For example, dark matter detection, yeah, that's typically also something that is happening in a relativistic regime, yeah. So that's so it's worth knowing this too. So just let me maybe start, yeah, with let me start with some a little bit formal introduction to that. Yeah. So, or maybe let's write it as action before X. So let's consider the action for a fermion. C bar d psi minus mc squared minus c4 c to the fourth and so on. So yes, there is some EFT for the fermion, and so far when we are discussing relativistic theories, yeah, we're using this kind of EFT expansion, yeah, where the expansion was in the according to the canonical dimension of the field, and you can justify it like a bit more formally, yeah, but you by the following argument, yeah, you can imagine that you are scaling all the momenta in the theory by some common parameter xi, and that is so xi equals to 0 is infrared and xi goes to infinity is UV, yeah? And simultaneously, yeah, we will okay, that also means that x goes to xi minus 1 x, and simultaneously you can we will scale the fermion field as with 3/2. The reason why I chose 3/2 here is that I want in the usual relativistic scaling, I don't want this term to, I mean, I want this term to not to scale so as to set a reference frame. Yeah, so you normally, yeah, you expect, yeah, that this kinetic term will dominate your path integral, and so we are just say it not to scale, and then we will be able to compare every term, the contribution of every term with respect to this term. So So if we do this scaling, yeah, then as promised, yeah, the first term doesn't scale, and it doesn't scale because you get psi minus 4 from the measure, psi to 3 from fields, and then there is derivative, yeah, so that's like momentum, so it's another psi, and so that 4 minus 4 is 0. On the other hand, if you do the same thing, so this will scale like psi to the 3, and then you get psi minus 4 from here, so you're getting one spare psi minus 1, and then you for this term you get psi to the 6, so this goes like c4 psi squared phi to the 4th plus. So yeah, and this is the rationale for the relativistic power accounting. So if you go to UV, those terms become more and more important, yeah, the one that have higher dimensions. But if you go towards infrared, so psi equals to 0, those all of these terms that have higher dimensions, that are high dimensional, become less and less important. Yeah, so their contribution, yeah, to the processes should be so this terms, yeah, in the EFT jargon, yeah, they're called irrelevant. On the other hand, this one is the mass term, yeah, is qualitatively different, yeah, because it becomes less important as you go to UV. That's understandable, yeah, because then you can treat the particle as masses. And then if you go to towards infrared, it becomes more and more important. So you could so at some point, this term and this term become comparable, yeah, as you go to the infrared, and that's where you go to the non-relativistic regime, and that's actually when so you have a cancellation between this kinetic term and the mass term. So actually, what happens is that in this regime you have to modify your scaling laws, and we'll see what kind of scaling laws you get in the non-relativistic regime. So you have to, in the non-relativistic regime, your power accounting will be modified so as to take into account that you have these large cancellations, or you can have cancellations between the kinetic term and the mass term. So I will demonstrate it, yeah, how to go to this non-relativistic regime in a more formal way, using the theory of a Dirac fermion. Yeah, so the Dirac fermion, in my notation, yeah, is the pair F and F bar C. So you have two. You have two component fermions, yeah, and actually that will be one situation where this kind of notations will be more revealing, yeah, than the standard Dirac notation. Now, my Lagrangian is, as usual, not C bar, sigma mu, d mu. These are the kinetic terms. Fc, sigma mu, d mu, F bar C, and then there is mass terms minus M FCF minus M F bar C. Yeah, so this is the free Dirac Lagrange. So this fields F and F bar C, yeah, then you can write it as you can write the expansion into the creation annihilation operators. I will call them ladder operators because when you say creation annihilation, it's always too long. So I will call it the expansion to the ladder operators. It has this form: e2 minus akx xk and ak plus e2 ikx yk bk dagger. Okay? And similarly for F bar C is if k e2 minus ikx yk bar ik dagger sorry k plus e2 ikx xk k bar BK dagger. Yeah, so this is the expansion into the ladder operators. This is the integration measure. Yeah, so this is a shorthand for d3k over 2 pi cube to ek, and then ek is square root of k squared plus m squared. Yeah, so yeah, that won't be very, very important. Yeah, then this is important. Yeah, that we integrate over k. So this is, yeah, these are the variables that we use in the for the relativistic calculations. But there is a you notice that both of these fields, they contain particles and antiparticles. Yeah, so this AK is the operator that annihilates particles, and BK is the operator that creates antiparticles. Yeah, so the field F annihilates, so contains both particles and antiparticles. On the other hand, when you work in the non-relativistic regime, you would like to have something that is more. So you typically you don't create particles and antiparticle pairs. Yeah, so you usually work with one type of matter, like typically matter in our part of the world, and so it's not. It might not be the optimal description. Yeah, that you have a fields that are contain both antimatter and antimatter. So we can change variables, yeah, and we can define new fields, yeah. So we can find some combination, yeah, some of like one sigma delta f plus 1 minus I over 2m sigma delta f bar c. So if you take a combination of the two, yeah, this combination actually projects out the antiparticles. Yeah, so this is maybe something that is more useful, yeah, for the non-relativistic calculations. And how do you see it? Yeah, so you just have to plug in this this expansion. Yeah, so let's say it's the star is equal to, and then we'll have a integral over d phi k, and then let's just focus maybe on what happens here with the antiparticles. So we have the k dagger, and then we'll have, so first term, yeah, does nothing, so you'll have yk, and the second term is a derivative, yeah, so it will act to e to minus ikx. So maybe I should say this as so these things here, there should be arrows. Yeah, I just don't have time to write arrows normally, so I would just put the bar as is often done. And so these are spatial derivatives. Yeah, m is the mass. Yeah, here. So now with the spatial derivatives will act on e to minus k spatial x. So you will get plus so you could get y k one to x, and then you say, and then you get something like k times sigma over 2m, yeah, y k, and then you will get from this second term, you will get plus x bar k, and then it's the same, but now you have you'll have a minus sign, k times sigma over 2m x bar k. And now what you have to do is you have to use the Dirac equations. So these are the spinor polarization functions. Yeah, so they satisfy the Dirac equation. So the Dirac equation is like in the relativistic way, if you write it, K sigma mu yk is equal to minus m x bar k, and the same for K mu sigma mu x bar k is equal to minus m yk. So what we have, yeah, we don't have the full relativistic contraction here. We only have the spatial part of that. So we have to, from this, we have to write the equation for the spatial part. Yeah, so it will be K sigma y K is equal to minus energy yk minus m x bar k, and the same for from this one, K sigma x bar k equals K x bar k plus m yk. So so you see where it comes from, yeah. So this is just k. So k0 times sigma 0. Sigma 0 is 1, and k0 is ek, and then I pull it on the right hand side. Yeah. So this is just unfolded this relativistic contraction. So we can replace it here, and then we get is equal to sorry. So I forgot to say. So I will. There is also the part, yeah, with a, yeah, but with ak e to minus akx, but I will not be tracing that there because, yeah, so just I mean, if you look at the notes, yeah, I trace both of them, yeah, but yeah, I will be I just want to show you that you project out the antiparticles this way. So, yeah. Yeah, I think it's correct. Sorry, but it's actually, it should be this. So this is the correct equation. Sorry. And yes, thanks, thank you. Okay, so then I will have this is equal to d phi k e to a chi x dk dagger, and then okay, I do nothing with it. Okay, and then when I act on the k sigma x bar k, I'm getting something that is so that will be minus 1/2 minus 1/2 yk, so acting from here, and acting on k sigma yk, I'm getting minus yk over 2m. Okay, and then the same will be, I will have x bar k, and then once, okay, I will get minus ek over 2m x bar k, and then last thing, I also have to hit here, and I get minus 1/2 x bar k. So this calculation, yeah, was to, and then there is a part, yeah, with e to minus akx ak, and then there is something, yeah. So the point is that you see, like to linear order in momentum in k, this is 0, yeah, because we have so we have this kind of an expression, yk 1k 1/2 minus ek over 2m, yes, and then I expanding is equal to 1/2 1 minus 1 plus k squared over 2m squared, yeah, plus order of k4. So you see that what I achieved here, yeah, is that this thing cancel at linear order in k. They don't cancel at quadratic order in k because I only define this combination to linear order in derivatives. Yes, so I could continue like that, yeah, and then add in this combination, yeah, the term with 2 derivatives, yeah, with 3 derivatives and so on, and make sure, yeah, that I project out the antiparticle at any order. So this is a bit tedious, yeah, but there is, of course, there is no rocket science here. So, but, so all in all, yeah, and there is, from maybe from this calculation on the blackboard, you don't see that I don't, when I take this combination, I don't project at the same time the particle. But yeah, this is just what happens is that for particle polarization, spinor polarization functions, yeah, there will be a different sign somewhere, yeah, and instead of 1/2 minus ek, 1/2 minus ek, you will get 1/2 plus ek, yeah, and that's this thing will add up instead of. So what I wanted to do this, yeah, is just to motivate, yeah, this kind of a definition, yeah, of the non-relativistic field into IMT over square root of 2, and then I can 1 plus I over 2m sigma delta f plus 1 minus I sigma delta over 2m f bar c, and phi c dagger is equal to am anti over square root of 2 minus 1 plus e over 2, well, no, minus e plus 1 minus e over 2m sigma delta f minus 1 plus I over 2m sigma delta f plus. So the thing is that, so all in all, yeah, I can define new sets of variables, and this is plus order delta squared plus order delta squared. So I can define this kind of transformation, yeah, that's at up to linear order in spatial derivatives, or up to linear order in momentum projects out the antiparticles. Now I also did something more here. Yeah, I added, so this is my choice. Yeah, so I'm just defining this. So this is my choice. I added this factor e to IMT, and the motivation for that, yeah, the heuristic motivation is the following. Yes, that this field, yeah, will have so this field phi, yeah, will be depending on particles like this, ak e2 minus akx, which in particular contains e2 akt. So then when I multiply it by EIM, I will get instead E2, yeah, plus IMT. So instead of getting the relativistic energy here, also, so this field will not oscillate with relativistic energy, but it will oscillate with non-relativistic kinetic energy. Yeah, it's just again the definition. Yeah, that will be very, very convenient in the following. Okay, so already used all blackboards. Good. Maybe. And you can also invert this. You can maybe invert this transformation. Is it here? This next page. For here. I can invert this transformation. So instead of expressing the non-relativistic field as a combination, yeah, of the left-handed and right-handed Dirac spinor, yeah, I can express the Dirac spinor minus EMT 1 plus I over 2m sigma delta psi minus E2 IMP minus E over 2m sigma delta psi C dagger. Square root of 2 into minus IMP 1 minus E over 2m sigma delta psi plus into IMP 1 plus I over 2m sigma delta psi C dagger. And I should probably close the bracket here. Oh. Good. So all in all, yeah, so this is the transformation. This is everything is up to all the delta squared terms. This is a transformation that takes a Dirac field, relativistic Dirac field, and rewrites it in terms of non-relativistic psi and psi C fields. So as I said, the non-relativistic fields, yeah, are characterized by two things, yeah. So they only contain either particles or antiparticles. So, and then CC would have the same as, but KT plus IMT. But instead of the particle annihilation operator, it will have a creation antiparticle annihilation operator. So this is just a change of variables. Yeah. So when we discussed it a lot in EFT, you can always change variables in the EFT. There is nothing wrong. So the choice of variables is yours. What is maybe different about this choice of this change of variables is that I break Lorentz symmetry explicitly because I want to extract really the low energy physics, yeah, from these fields, separate particles from antiparticles, and also change sort of the nature of the field so that it doesn't oscillate quickly with the according to what is the largest scale in the problem, which is the mass, the rest mass. But instead, yeah, it will be behaving in a relativistic, like in non-relativistic physics, we'll be using the kinetic, non-relativistic kinetic energy and the AK, yeah, so plus K squared over 2m. Yeah, so instead of we'll be using just this part of the energy, and then we'll be ignoring, yeah, this dominant part of the energy. So yeah, and this here on this, I only defined this transformation to the up to the linear order. Indeed, you can actually so if you look at the, how do I go find my notes? Oh, yeah, if you look at the notes, and this transformation is also written here. Maybe it's a little bit better font. You see that, yeah, also there in the notes, I also went to the next order in the derivative expansion. Yeah, so, and you can like define it order by order. And there is a way to write it down up to all orders in delta, in nabla, but what you will get, yeah, is pretty complicated and not very revealing. Yes, I haven't written that. Yes. Good. Okay. So why would I do that? The reason is that the following: that if you now plug back, yeah, this change of variables into the original Lagrangian, let me first write you what you get. So you will get that Lagrangian, this Dirac. Okay, let's call it. Yeah, the Dirac Lagrangian that is written there on the top of the other blackboard will take in the new variables will be like this. This page. So that's okay. I just wanna check that I get all the signs correctly. Okay, but probably not. Oh, maybe I'll have it here. Anyway, with this, yeah, and then the same. C dagger dt c plus cc dagger c over 2m. So this is what you're getting, and then there are corrections of order derivative to the cube for that. But so what you get, what you got is that as I was advertising, particles and antiparticles are separated. Yeah, and then also because that's thanks to this this factor that I added, the psi field doesn't satisfy the Dirac equation. If you now calculate the what is the equation of motion that follows for the psi field, it's the equation of motion is psi is equal minus psi 2m. And you've seen this equation before, probably. Yeah, this is the Schrödinger equation. So this is the change of variables that takes you from the Dirac field. So from the 4-component Dirac field that satisfies both that describes both particles and antiparticles. It takes you to non-relativistic particle and non-relativistic antiparticle fields that satisfy the Schrödinger equation, and of course, yeah, that's the same equation you get for the antiparticle. Yeah, there is no difference. So you see that there's in most cases, yeah, you only want to work with particles because you will not have antiparticles in your experiment. So this transformation will be even simpler, yeah, because you just have to take the first half of it, and that's the whole point. So it's yeah, it will be a little bit of blackboard. I mean, it's if you insist, yeah, I can do this. I can prove it on the blackboard. But maybe if you don't insist, I will just prove it that the leading order terms in M cancel, yeah, with this transformation. Yeah, so we have just so that you see what is happening here. Yeah, so you have I psi bar sigma bar mu d mu f plus I psi c sigma bar mu d mu f bar c minus m fcf minus m f bar c. Yeah, so now I plug in this f, and then I will be interested only for the sake of this calculation. I will be interested only in that leading orders in M, which go like M to the power of 1. You can see more careful calculation in the notes. Yeah, so maybe I can scroll down so that. But yeah, you can do it more carefully. But at the leading order in M, so the only way to get M from this change of variables is when you have a time derivative will bring M down here, and here in this case your M is already there, so you don't have to do anything. So we write it down that this is E. So I'm plugging in this E2 minus EMT psi dagger, and then I have a sigma bar 0, which is just 1, the unit matrix, and then I have dt. Sorry, this should be like this: E2 minus EMT psi so that there is an equality, yeah, plus the same thing I'll have to do for the other guy. So I into a mt dt, sorry, psi dagger dt and e2. It's the same, yeah, minus imt psi. So then both of these terms are the same. There's 1 square root of 2, so I'll have 1/2, but they are the same. And then we'll have minus m FFC, yeah, will give me so 1/2 psi dagger psi, and then minus m half psi dagger psi. Yeah, so this factor of e to minus, so now you see that if I hit dt with the time derivative, I hit this factor, I pull down minus em, so it will, the whole thing will be proportional to m. So I'm getting here m psi dagger psi, and then I have minus m psi dagger psi is equal to 0. Yeah, so this is the change of variables where all the leading order terms in m cancel out. So in a sense, this you can think of it that this change of variables partly like integrates out high energy modes. Yeah, where the high energy is for non-relativistic physics is everything that goes like so the high energy scale for non-relativistic physics is m, the mass of the particle. So this sort of transformation, yeah, get rid of. And now you see how for example, how I get this Lagrangian in more detail. If time derivative attacks this piece instead of the exponential, then you're getting exactly this piece. Yeah? So you have already dt. And finally, yeah, and then you have to work a little bit harder, yeah, to go to see that what you really get is you're getting the nabla squared term, yeah, over 2m, yeah, because you have to go to higher orders, yeah, but it's something like it's a 10-minute calculation, yeah, that you can easily follow, yeah. There is nothing very complicated. Okay, so this is my free Lagrangian, yeah, for particles, antiparticles separated. Now you can go back a question. So what is the scaling here? Yeah. So this is the kinetic terms, and they are connected by the equations of motion. So we want some sort of a scaling, yeah, that where both of these terms behave in a similar way under scaling. So when I have a s equals int d for x I psi dagger dt psi plus psi dagger nabla squared psi over 2m. And then we will, again, we have x, or p goes to psi p, x goes to psi minus 1 p. And then I will choose the dimension of f psi, again, 3/2. Then the first term, oh, sorry. No, I did a very, very stupid thing. Okay, so let's do this, the momentum scale like before. So then we're getting a psi squared from here. And or maybe let's keep this kind of this. So let's keep this. So then we have psi to the 3 from here from okay. Let's do it like this. So now we have just trying to see how it is. So so this term only has so this whole thing, yeah, will be scaling as psi to the 5th, and then it means that the measure, yeah, if I want this not to scale, also the measure has to scale as psi to -5. So there will be psi to -3 from x's. It means that the time has to scale differently than space. So the x spatial will go like this, and time goes like psi minus 2 over t, right? So now the measure will scale as psi to minus 5, yeah, because I got this additional factor of psi from the time, and then this whole thing, yeah, is invariant under the scaling, and the same thing will be here. So this is simple. So this time derivative scaling will cancel the time scaling here, and then you have psi to the. So you have, anyways. You also have. I mean, or rather, it's also, this also scales as psi to the 3 times psi to the 2, and both terms scale the same way. So the most important, so the lesson here is that in non-relativistic physics, we have a different power counting. Yeah, before we were counting derivatives, the relativistic derivatives. Yeah, as that was our expansion. But here, the time derivative counts differently, weighs differently, yeah, than the space derivative, yeah, in the non-relativistic physics. Moreover, yeah, you see that I can always use this equation, yeah, to trade the time derivative into space derivative, yeah. So that will be the lowest order equation of motion. So when we write the interaction terms, yeah, we can write them as a expansion using only spatial derivatives, yeah, because we can always trade time derivatives, yeah, for two space derivatives. Okay, so that's the formalism. Yeah, so I was sort of trying to give you some flavor. Yeah, where does this kind of change of variable come from, and what does it achieve? Yeah, so this is. But you can also take just a point of view. Yeah, that okay. Here is the change of variables. I can do any change of variables in quantum field theory, and I do this change of variables, yeah, and I'll see what happens, yeah, and what happens, yeah, is exactly this separation of particles and antiparticles, and also you get a Schrödinger equation where you have a different scaling, yeah, for the space coordinates and the time coordinates. Okay, so now let's try to see some applications of that. Yeah, so I will just show you 2 applications. Yeah. Oh, maybe. Yeah. Probably good questions. Yeah. Yeah, I think so. Yeah. 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 I think that's fair to say. Yeah, that there can be systems, yeah, where the scaling is different. Yeah, you're right. Yeah, that I mean, you could also get this scaling, yeah, this relative scaling between the time and space, yeah, just from Schrödinger equation. You could also, or you can also view it, yeah, that energy, kinetic energy, yeah, is k squared over 2m, yeah. So this is time, 1 over time. This is 1 over space, yeah. So there is different way, yeah, to see where this different scaling comes from. Okay, so I wonder. So start with the first examples now, or come on, one quick question. No, not a little bit different. Yeah, so it's later. So I don't think I will get to that. So maybe since there is a question, I will show it. Yeah, on the just on the slide. So there is this. So the thing is that, yeah, for a scalar field, yeah, your equations of motion are second order. Yeah, so there's no way to have a change of variables, normal change of variables, to get to the first order equations. So you have to use a trick, and the trick is, yeah, sort of introduce this rewrite the Lagrangian. So you introduce canonical momentum pi, yeah, which is, yeah, and then you rewrite the Lagrangian this way. Yeah, so you rewrite this dt phi squared, yeah, in this funny way, yeah. And then you treat pi and phi as a different independent variables. and then you do a change of variables on this in this. Yeah. So you, of course, the equations of motions here are the same. Yeah. For in this Lagrangian in 336 and 337, and so they are equivalent. And here, yeah, and then you can do the change of variables. Yeah, that you define your particle and antiparticle field as a combination, yeah, of phi and pi, of and then or the other way around. Yeah, and then yeah, you can do this calculation. And even for scalar, it's a little bit the math is slightly simpler. Yeah, so you can show that what you get at the end, yeah, is something like that. Yeah, so you see that the this delta squared over 2m is just the first term in the expansion of rest energy minus total energy. Mm-hmm. 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 Yeah, but I think it's a sort of morally, it's the same thing. Yeah, so I'm just. So sort of this is the variables, yeah, in which the integrating out or averaging, yeah, and so I would call it integrating out scales that are larger than m, yeah, is particularly convenient. Yeah, you still, I mean, I haven't integrated out anything. I just changed variables for the moment. Yeah, so this is, but in these variables, yeah, integrating out, yeah, this high energy or stuff, yeah, is much more convenient. So it's most of the time it's just automatic. And yes, sometimes yeah, you also have to work a bit harder. Yeah, but this is actually the example of a scalar. Yeah, so you can show that. Yeah, so for example, you can that's a classical exercise to show that you don't have a cubic interaction in non-relativistic physics. Yeah, that doesn't exist. Yeah, and that you can do this change of variables, and then you see that you have this. The mixing between matter and antimatter and a bit weird factors, and but when you integrate out the high energy modes of the fields, yeah, then you're getting something that is a quartic interaction at the end of the day. Okay, good. Is there more questions? Yeah. No, so well, they scale the same way because they are connected, yeah, by this equation, yeah. So sort of like your oscillations, yeah, in the system, yeah, will satisfy this equation, yeah. So you want the so these two terms are not independent, and then the choice, yeah, that it scales as psi to the zero. That's just convention, yeah. But yeah, Schrödinger equation, yeah, relates, yeah, this term and this term. Good. So what do you prefer? Like 10 minutes break now and come back to the examples, or go on now? Great. Okay. 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 Good. Okay. So let's restart. So I wanna talk now about some simple applications of the non-relativistic formalism. So this will be the first example. Will be coupling to electromagnetic field. Yeah. So you have this is a minimal coupling of a Dirac fermion of charge Q to the photon. Note that yeah, I said I do non-relativistic, but non-relativistic refers to the fermions. So we are at energies, yeah, well below the fermion mass, or momentum below the fermion mass. But I can have relativistic stuff around because that's what happens. Yeah, we have we live in an relativistic world, but there are relativistic photons flying around. Yeah, so that's but it's okay. I this is just a change of variables. Yes, I can do. I didn't really commit to low energies. I just chose variables that are convenient for low energies. So now what will happen if we do this change of variables, yeah, in this minimal coupling? So then we have to just calculate this bilinears. So that's this f sigma bar mu f, yeah, will be equal to, so have 1/2 from the square root of 2. The e2 minus imt's will cancel because, yeah, we don't have any time derivatives. We don't have to worry about those. And then we will have 1 plus I over 2m sigma delta. Oh, okay, I should maybe write it like that. Psi dagger minus e over 2m delta psi dagger sigma. Then I have a sigma bar mu, and then I have f psi plus I over 2m sigma delta psi sigma nabla psi. Okay. I don't need this, yeah, I think. So I just expand it, yeah, and then I get 1/2 psi dagger sigma bar mu psi, and then I have minus I over 2m psi dagger sigma. Yeah, the only thing is that this bar is different. Yeah, if the bar on sigma mu is a different thing than the arrow over sigma. Yeah, so this one. Yeah, this is, yeah, if you look at the notes, yeah, these things are separated. Yeah, but I don't know how to write nicely bold font on the blackboard. Well, here and then there'll be plus I over 2m psi dagger. Oh, that should be dagger, yeah. No. Psi dagger. Psi dagger sigma bar mu sigma delta psi. Okay, and then higher order terms, yeah, that I won't be tracing. The same thing for the other bilinear. F bar c is equal to. So this is the calculation is exactly the same, except that for the right-handed guy, yeah, there is a difference, yeah, on this I. So this terms with I will have a flipped sign, and then I have a different kind of. I don't have a sigma with a bar, but sigma without bar, yeah. So which is of course will be important. Minus I over 2m psi dagger sigma mu sigma delta psi. So it's the same. I just change I into minus I, and I change sigma bar to sigma. So now we can what we have is the sum. Yeah, it's a vector sum of the two pieces, left and right. So we have to add them up. So actually the sum will be somewhat different whether the mu equals 0. So let's take whether mu equals 0 or mu is a spatial index. So if it's a time index, we have this plus psi sigma 0 psi bar c, yeah, psi c psi bar c is equal. So we add the sum, those two first. So sigma 0 and sigma bar 0 is just 1. So we'll have psi dagger psi, and then again the sigma bar and sigma is the same thing. So this terms with the derivatives here only differ by the sign. So they cancel out. Yeah. So this 0 component is just this. For the other guy. Okay, maybe I want to have this psi bar sigma bar k psi plus psi c sigma k psi bar c So let me just be here. Psi bar minus sigma k f plus psi c sigma k psi bar c. So you see that now we have to actually subtract, yeah, will be subtract, or maybe, yeah. So again, maybe I don't write it like this, yeah. So okay. So, but the important thing is that that there is this sigma bar k is really minus sigma k, yeah. So it will be. So now when we add these two leading order pieces, they will now cancel, yeah, because sigma bar k is minus sigma k, yeah. So there will be no leading order piece. So this will only contain the derivative pieces, and it will be given by okay, I think, sorry, so I lost, so this is, I did made a mistake here, yeah. So I lost 1/2 because there is 1/2 from that I have to keep in front. So I correct it, yeah. And then I'll have my plus I over 2m nabla psi dagger sigma sigma k psi minus I over 2m psi dagger sigma k sigma delta psi. So this bilinear is this. We can somewhat simplify it. I mean, I could simplify it if I had some blackboard. So let's continue here. So we can write it, yeah. So maybe let's write it just again to be, let's do it I over 2m. And we write it like this, yeah. So let's do indices, sigma n, sigma k psi minus psi dagger sigma k sigma n delta n psi. And then I will use the usual identity, the identity for the sigma matrix, yeah, that's sigma n sigma k is equal to delta nk plus I epsilon nkm sigma m. And then I got, so we'll have a term with delta nk. So we'll have something like that, I over 2m sigma nk. There will be this, yes, psi dagger delta k psi. And in a self-explanatory way, I just wrote it, yeah, in a little bit condensed form, which this means that derivative acts here minus derivative acts here, yeah. So that's the usual. And then I have to also I'll have this other term, so it will be minus 1 over 2m. And 1 over minus 1 over 2m, and epsilon nkm delta n psi dagger psi sigma m psi, and then I will have minus, yeah, so plus 1 over 2m epsilon nkm psi dagger sigma m delta n psi. So this is what we are getting. Okay, so now we have everything, yeah. So let's put this results in the Lagrangian, yeah, and then we're getting the first term is minus QE A0 psi dagger psi, yeah. So this is how non-relativistic field interacts with the electromagnetic potential. Yeah, the zero component, yeah, of A is just the potential. Yeah, and this is not surprising. Yeah, so this when you then derive equations of motion, yeah, this will be just multiplicative, yeah. So it will be the usual V in the Schrödinger equation. But interaction, yeah, with the vector component is less trivial, as you might remember from quantum mechanics classes, yeah. And then we'll have plus QA E AK, and then I have to plug in this all of this. Minus I over 2m psi dagger delta k psi, and then plus, and then, okay, so then I can also compactify this. I can write it as epsilon nkm. Okay, maybe I can over 2m delta n psi dagger sigma m psi. Oh, okay. Yeah, I just put those two terms. So these two terms are total derivatives. You might think, yeah, that there is. Okay, no, but I screwed up the sign somewhere. But yeah, because okay, you see that there is here. You have a kn in this piece. Wait, just lost here. Here you have an nk in this, where the derivative acts on this. Okay, so that's with nk, and here you have a kn. So I made a mistake here, yeah, because there is the index k is either after or before, yeah, the other sigma with a couple that is contracted to the derivative. Okay, so this is what we should get. Minus 1 over 2m, so nkm, and then I should have minus here, yeah, okay, fully. So okay, so we'll see later, yeah, if I got the correct. So here nothing changes, and in the second term nothing changes. And in the last term, I can integrate by parts, yeah, and then I will have plus QE over 2m epsilon nkm delta n ak psi dagger sigma m psi minus e. So now this is a rotation, yeah, of the this is the rotation of the vector potential. So this is the magnetic field. So at the end of the day, yeah, we see that the minimal potential is this minus E. So minimal interaction of the electromagnetic field with a non-relativistic particle is this. And then there is, we can write it like this, plus QE over M BK C dagger sigma K psi. Okay, good. So I lost the 2 because I wanted to put it 2 here and I forgot. So you see, so this is again interaction of the relativistic particle with a potential, with a electromagnetic potential. It's just like a potential in the Schrödinger equation. Yeah. So if you now derive the equation of motion, yeah, you will get this multiplicative term A0 times psi. Yeah. So you can maybe yeah. This looks weird, but this is how it is. Yeah. So this is how when you want to write down an interaction, yeah, of the vector potential, yeah, with the into the Schrödinger equation, this is how it will enter. Yeah. And this is how it is. And there is a funny term. There's another term that popped out here. You see that this, you can call it a spin operator, yeah, this sigma k. this is the, so this size, yeah, maybe I haven't stressed it, yeah, but you know, the F and F bar C, they were two component spinors, so this psi's are two component spinors too. And there is sigma is acting on the spin indices. So, and then if you have if this psi has an upper component, yeah, that for example, sigma 3 will return 1, and if it has a lower component, yeah, it will return minus 1. Yeah, so this is a spin. So this is a coupling of a spin of the particle to the magnetic field. So this interaction, this describes the magnetic dipole moment. And then you're getting what is the coefficient here for this. So you're getting that mu equals q e over m for a minimally coupled particle, and this now for reasons that are completely unknown to me, I usually write it like that. Yeah, q over 2. I mean, this is the magneton, and this is the gyromagnetic factor g equals 2. Yeah, so that's so this calculation shows you, yeah, that spin 1/2 fermion, yeah, has g equals 2. Yeah, and in fact, any minimally coupled particle, like of any spin, yeah, will have g equals 2. Okay, so maybe I will not. Okay, let's do one more little thing, yeah, in this vein, yeah. So what if you don't, if you have a non-minimal coupling, what will you get? So let's add plus c f mu nu psi, okay, f c sigma mu nu f plus Hermitian conjugate. So this is the non-minimal coupling to electromagnetic field. Yeah, this is a higher derivative. This dimension of c is 1 over mass. So this is once you add this sort of a coupling, yeah, the theory becomes non-renormalizable. But yeah, this is something, yeah, that you can you can add. And then what does it translate to? So again, we have to, I forgot to say the sigma mu nu is defined as I over half sigma mu sigma bar nu minus sigma nu sigma bar mu. Wow. That's the definition of this. So now if you want to, what is fc sigma 0 k f? That's I fc sigma 0 sigma bar kf, so it's equal to minus I fc sigma kf. And now you have to plug in these definitions, but now we don't have to really deal with derivative terms because we already have, effectively, we have one derivative here, yeah? So you'll see that you don't need to go to higher, so we just have to plug psi. So this is just minus I half psi c sigma k psi, and the other for the other guy, yeah, you get that this is equal to I fc sigma k sigma bar l f is equal to minus minus 1 fc minus 1 epsilon klm fc sigma bar m fc, and then it is equal to minus epsilon plus epsilon klm psi sigma do I have it right? Okay, so now we can plug it into the this Lagrangian, yeah, to see what we get. And so we'll have C F mu nu F C. I just forgot the factor. When I plug in here, I should put factor 1/2. Yeah, so that's to be correct. FC sigma mu nu F is equal. So first, it will so we can write it as minus C F0. Oh, yeah, it's not minus. Yeah. CF0K FC sigma 0K F, and then there will be a factor of 2 here, yeah, because you can have 0K and K0, and then there will be plus 2C F KL FC sigma KL F. So now this is a F0K is the electric field. So this is a, and here we have to, this will be again minus I sigma 0 sigma bar, so plus I sigma 0 sigma bar K, so it's equal to minus I sigma 0 sigma K. So we have what we'll get, yeah, is equal to should have got this. No, so sorry. I mean, I got confused. Okay, so we're getting here as minus I C AK psi C sigma K psi, and then we'll get from the other term. This will be the spatial components, yeah, of F that these are related to B. So we will get plus. Where were we? I think just to be sure, yeah, that I haven't done anything, and then we get minus C where is it? Minus C sigma BK C dagger C dagger sigma K. So you see that you have this nonlinear coupling gives you the electric field coupled to spin and the magnetic field coupled to spin. So then when you take this is taken with the Hermitian conjugate. So this plus HC is equal to imaginary part of C EK psi dagger sigma K C times 2 and plus 2 real part of C BK psi dagger sigma K psi. So this term corrects G minus 2. So if you have this kind of interaction in the Lagrangian, then you have an anomalous contribution to the magnetic moment of a particle. And if you have imagine this kind of interaction with the imaginary Wilson coefficient, then you're getting the electric dipole moment of a particle, which is a CP violating effect. Yeah, so it has never been seen, yeah, for any elementary particle. We've never seen an electric dipole moment for any elementary or sufficiently simply composite. Yeah, so you have to go to molecules, yeah, to actually see electric dipole moments. Yeah, so that's something. Okay, so this is the so this was supposed to show, yeah, that you can. This is the formalism, yeah, that allows you to easily recover, yeah, something that you know, things you know about particles, yeah, that how they couple to electromagnetic field, yeah, that what is the magnetic moment, yeah, of spin 1/2 fermions, and what is the what is that this kind of interaction, yeah, is related to anomalous magnetic and electric dipole moments. Yeah, so this is and you obtain it pretty easily, yeah, by this change of variables. Let me go to another application. Maybe let's start with this blackboard. Let me go to another application in that is related to beta decay. So we talk about beta decay in the first lecture, and then we discussed, yeah, that the Fermi theory, which you get from integrating out the W bosons from the standard model and then crossing the boundary between perturbative and non-perturbative, so you change variables from quarks to nucleons. Your effective theory to describe beta decay will be this. And then you have P bar sigma bar mu n plus PC sigma mu n bar C. And then you have another term like this, the same leptonic part, but a different sign in between here. And then you have some. So this is the Fermi theory. So here we can be a little bit more ambitious and do more EFT. So this is not the all possible interactions between the nucleons and leptons that you can imagine at the zero derivative level. So at the same level in the EFT expansion, you can add more interactions. And for example, you can add so-called scalar interaction, EC nu. So where you have PCN plus P bar and bar C. Or you can add a pseudoscalar interaction. And then you can also add a tensor interaction. Sigma bar mu PC sigma. No. Okay. So yeah. This is the neutrino field, yeah, and this is index, yeah, just not to mix up the two. So this is this 5 kind of interactions that you can imagine in principle. So at the early days of beta decay, this is what people were working with. So this Lagrangian was written first by Li and Yang in '56. Yeah, so I think this is really, if you have a chance, yeah, you should read this paper, yeah, because it's super modern in the way they're thinking. So they were saying, we don't know really what the interactions are, so let's write all possible interactions, yeah, at this order in the EFT expansion, and then let the experiment see which ones are actually relevant. They also said that in principle, yeah, at this level you can write parity violating interactions, yeah, and so in principle, beta decay experiment should look for parity violation, yeah, which was something that nobody had thought nobody had thought before. So what they wrote was basically this, except for in those days, yeah, people didn't know that there's only left-handed neutrino, yeah, so they had both left-handed and right-handed neutrinos, so they had instead of 5 interactions, they had 10 interactions, yeah, because and then parity was conserved, yeah, if the left-handed neutrino and right-handed neutrino interact in the same way, yeah, so which of course turned out to be maximally violated. So let me again apply this kind of change of variables here. It will be, but it will be even simpler because I will not be now I make it even simpler. Yeah, I will not be tracing derivative terms. Yeah, so I will be tracing only the leading term here. So what do we? So what do we have if we change these variables? One more thing I will assume, yeah, that the proton and neutron have the same mass. Yeah, of course they don't. Yeah, but the difference is tiny. The difference is related to isospin breaking. So in the first approximation, you can assume that they have the same mass, and then this E2 IMT factors, yeah, they will cancel out in this after this change of variables. So I will not have to deal with them. So what do we have? Yeah, so. Let's start with the vector interaction. We actually calculated it already, yeah, when we did the calculation for the we were calculating the coupling to the minimal coupling of electromagnetic field to a spin 1 particle. Just 10 minutes ago, we calculated that, yeah, and this is equal simply psi p dagger psi n. Yeah, so now the only difference is that now I have a separate non-relativistic field, yeah, for the neutron and the proton. Yes, yeah, so I make this change of variables, but separately for proton and neutron. On the other hand, yeah, we also calculated that this sigma bar k is equal to, that was something that was of the order of the derivative, of the spatial derivative. Similarly, we haven't calculated it, but it's I should have this sigma bar kn minus. So let's go to the axial part. It's the sigma k and bar c. So again, sigma bar is minus sigma k. So this is really not a difference, but a sum. And then when you sum, you will get this. On the other hand, p bar sigma bar 0 and minus pc sigma 0 and bar c is equal of delta. So for the Fermi theory, you already know, yeah, what are the interactions. So maybe let's start writing them somewhere here, so that we don't get completely lost. So if we plug it in, yeah, in the first two terms, yeah, we have lambda is minus CV, epsilon bar sigma bar 0 nu, and then times Cp dagger Cn. And then we'll have a second term. Actually, sorry, I think there should be a minus sign here. So that, and then we have a second term. We'll get plus Ca epsilon bar sigma bar k nu Cp dagger sigma k Cn. So this has the same content, yeah, as what was discussing as the Fermi theory in the relativistic regime. You see that you have like this two kind of hadronic structures or nucleon structures. Yeah, you have the scalar and vector kind of contraction of those two, and that in fact gives you different kind of transitions. Yeah, or in nuclear physics. Yeah, this is if this operator mediates a transition, this is called a Fermi transition, and this is if this operator mediates the transition, it's called a Gamow-Teller transition. This kind of so for if you have a spin 0 nuclei, which is very, very common for nuclei, the matrix element of spin 0 nuclei if both the mother and the daughter particle in the beta decay will have a spin 0, then the matrix element of this guy will be 0 because this is a vector. And there is so in the zero recurrent limit there is no vector that you have in your problem. So this has to be 0. And then this transition of spin 0 between the spin 0 nuclei are only mediated by the Fermi term. On the other hand, if you have higher spin nuclei that go to the same spin nuclei, then always you have both terms contributing to the transition. But then there are transitions where only this term contributes, and this is called these are called pure Gamow-Teller transitions, and this happens if you have a if your mother nucleus and the daughter nucleus have spins that differ by 1. If they differ by 1, then the matrix element of this guy will be 0, and this can be understood because this is just a sort of scalar operator and it doesn't touch the spin, and this is a spin 1 operator and it can change the spin of the state by ±1. Yeah, so this mediates transitions with delta j equals ±1 and 0, and this mediates transitions with delta j equals 0. And then if your mother and daughter have a spin different than 1, then in the theoretical approximation, you're getting that the transitions cannot happen, and these are called forbidden transition. Although they are not really forbidden, because there are recall effects. So the forbidden are it's just a funny misnomer, but they do happen, but they happen more slowly because they are mediated by higher order operators in this EFT expansion. Or maybe this was not completely correct. They are mediated by higher order operators or by recall effects in this matrix elements. So okay, so what I wanted to say, I wanted to do just say something. How much more difficult is to do the more complete EFT compared to just what Fermi did. So let's calculate this. What would be this? The scalar matrix, the scalar bilinear in non-relativistic variables. So we plug in these variables, and we plug psi p dagger, so it will be 1/2 because of this 1/√2 psi n, and then from the other term we have to add 1 psi p dagger psi n. So it's equal to, that was the most complicated calculation I did in my life, and that's the so you see that you got the same as for the vector. So now if you wanna write down this E bar, sorry, it will be EC nu psi p dagger psi n. And so you see that scalar and vector are very, very, very similar. So they correspond to the same matrix element in the non-relativistic limit, and they only differ by the fact that in this case you have a left-handed electron that participates, and in this case you have a right-handed electron that participates. So that's the only difference between a vector and scalar. And so that's this way you can understood that why in the early days of like in the 50s, there was a confusion whether the interactions are vector or scalar, because they are very, very much the same. And then if you read, you must be joking, Feynman, he was very proud that when he realized, that it doesn't have to be, it's vector and axial and not scalar and tensor as people thought initially, because so the only way you can recognize it, you can see the differences. You really have to be sensitive to this fact that you have this. In one case, you have a helicity flip, and in the other case, you don't have it. So the difference is there. If you calculate this will lead to a different distributions, like for example, like a bit different energy spectrum, but the difference is rather subtle, and it's easy to make a mistake. And people did make this mistake, in the early days. So what about pseudoscalar? let's do another very complicated calculation. Psi n minus 1/2 psi Pythagoras psi n, which is 0. And of course, we only did the calculation up to this order. Yeah, so pseudoscalar doesn't contribute at all in the leading order in the EFT, non-relativistic EFT expansion. Yes, pseudoscalar doesn't you don't have any interaction. It only corresponds at subleading. It only contributes at subleading order. So when you do experiments in beta decay to the leading order, you don't really probe this kind of pseudoscalar interactions. Yeah, but fortunately, yeah, there are other ways, yeah, to probe it. And the last one, the tensor, yeah, this is the most pesky, but yeah, so let's try to do it. Sigma 0 k nu, yeah, sorry, nu, but why who wrote nu here? N is equal to I PC minus I PC sigma k n is equal to minus I is equal to minus I over half psi Pythagoras sigma k Cn. So you see that this matrix element looks like this one. Let me just not do, because yeah, if I do this, so what you have to do, yeah, you also have to show that this is, I mean, this is something proportional to epsilon KL m psi Pythagoras Cn sigma k Cn with one sign or the other. It's easy. And then you plug it into the, where is my, into the Lagrangian, yeah. Then you also have to rewrite the sigma mu nu, yeah, with in indices, yeah, with blah, blah, blah. And then you find that this is equal to plus Ct epsilon c sigma 0 sigma bar k nu times c Pythagoras sigma k psi n. Yeah, so as I said, the tensor interactions are very much like axial. Again, the difference is that the chirality of the electron that is. And then again, people, yeah, so in the early days, yeah, I mean, like for example, if you read the Wu paper about the experimental discovery, yeah, they interpret it, yeah, in terms of the tensor coefficients, yeah, rather than the axial coefficients, because they're using some pure Gamow-Tellez transition, and they comment, yeah, what the value of Ct has to be, because at the time people thought that, yeah, the interactions are scalar tensor rather than vector axial, yeah, and that was only a year later that it was understood that they are vector axial instead of scalar tensor. So okay, so this is the this is how you apply this formalism, yeah, to the beta decay. You see that you can systematically improve it. Yeah, you don't have to stop at the leading order in the derivative expansion. So this is an EFT, yeah, and then there will be corrections that are of order delta over mn, yeah, where the n is the nucleon mass. Nucleon mass is 1 GeV, yeah, and the typical momentum exchange in beta decay is of the order of 1 to 10 MeV. So this is a good expansion, yeah. But if you want to do precision physics, yeah, sometimes precision is of the order of per mil or 10 to minus 4. You have to also include the subleading effects, yeah. Some of the subleading effects are sometimes seen at the level, yeah, of 1 to sigma in this kind of experiments. Yes, it's worth including them, yeah, to get the correct picture. Okay, so I think this would be it for now. As I said, I have only this the one more thing that I could talk about, yeah, but I don't think there is time for that. Yeah, is the the transformations, yeah, for yeah, one thing I can, yeah. So for example, I can comment, yeah, when if you look at the spin zero kind of transitions, yeah, you can look at the 10, you will have a very subtle differences, yeah, for between the vector and scalar contributions, yeah, which are in the sign of this term that is a product of the electron and the neutrino momenta, yeah. So you can, in principle, if you measure it, measure what is the sign in the distributions, yeah, you can distinguish between vector and scalar. And yeah, the one more thing that is in the notes, yeah, is what already was alluded in the question, yes, how you deal with this kind of, with this change of variables for bosonic theories, yeah, where you have to start with the, where you're starting with a two derivative relativistic equation. So in order to go to one derivative Schrödinger equation, yeah, you have to do a little bit of a formalism, yeah, to introduce this canonical momentum and then change, to do the canonical change of variables in the field and the canonical momentum space, yeah, and that, but yeah, that works more or less the same. Maybe one more thing that is worth noticing here is that when you do this change of variables here for a scalar, it has this form, and then there is a square root of m here in the denominator. So since the dimension of phi, of the scalar phi, is 1, and there is square root of m here, so the dimension of the field has to be 3/2, just like for a fermion. So it means that the non-relativistic scalar field has dimension 3/2, and then the consequences, yeah, is that for example, phi to the 4 interaction, of psi to the 4 interaction. So phi to the 4 interaction is marginal, yeah, in the relativistic theory, in the sense that it's important both in the UV and the infrared in more or less the same way. And psi to the 4, yeah, is because this has dimension 3/2, is suppressed, yeah, by the 1/m². So this is a irrelevant interaction. Yes, a self-interaction of a scalar, also for a fermion that might be more obvious, yeah, but also for a scalar, self-interaction is an irrelevant operator in the non-relativistic regime. And yeah, it makes sense, yeah. So maybe you remember that this kind of self-interaction corresponds to a delta function potential, yeah. So this is something that is less important than, for example, long-range forces, yeah, that are controlling, yeah, really the behavior, yeah, of atoms, for example. Yeah, so that's that makes sense. Yeah, but this is a simple conclusion that you get, yeah, from this kind of exercise. Okay, let me stop here, and we'll continue tomorrow. Yeah, so maybe yeah, so yeah, just a second. Just wanted, before I forget, I wanted to say, so tomorrow we'll have the two lectures. Yeah, the first is about neutrinos, the second about on-shell theories. So if nobody has ever seen on-shell formalism, I mean, if somebody has never seen on-shell formalism, I recommend to read maybe the just the first section of the notes, yeah, before that. So this is it's called lightning introduction, yeah. So it's like 2-3 pages. Of course, I will go through this also, but if you see it first time, you might be probably decoupled very immediately, yeah. But if you maybe read it once and then you hear about it twice, you'll be able to follow, yeah, the rest of the lecture. Okay. There was a question. So I think I didn't understand the yes. Oh yeah, yeah. So it's the same. It's the same thing. Yeah. So when you calculate the matrix element, yeah, of this operator between the nuclear states, yeah. So this is how the isospin current, or the one component of the isospin current, looks like in the non-relativistic regime. Yeah, and you have the same thing. Yeah, that this matrix element. This matrix element, yeah, so you have a nuclear state, psi p dagger, psi n, and then nuclear prime is given by something square root of jj plus 1 minus j3 plus 1. And this is the isospin of this, and you assume that your transition doesn't change. So this is true, yeah, if the transition doesn't violate. So it's within the isospin multiplet, and J3 is the Z component, yeah, of the isospin. So this changes by 1, yeah, in this transition, like between the proton and neutron, for example, yeah. So if you know to which isospin multiplet belongs your parent and daughter nucleus, yeah, then you can calculate this matrix element up to isospin breaking corrections, which are percent level. Just a vector, and you see that for the scalar it's the same, yeah. So the scalar and vector give you the same matrix elements, yeah, for the hadronic side. For the axial, we don't know, yeah. So this is something that this is brown mark, yeah. So if you put the same thing here but with this, so this is there is a little bit of a discussion in the notes, yeah, which I was not going through, but this has to be proportional to some rotation operator, yeah. So that's that you can express it in Clebsch-Gordon coefficients, yeah, and it will be some generator of the rotations here. But then there will be some coefficient here that you don't know, and it's sort of random, yeah. So if you look at it, yeah, it will be different for different nuclei. So you only know it for neutron, yeah, because then it's perturbative in this EFT. So this coefficient is, I think, like square root of 3, yeah, for neutron, and then it just goes. It's order 1 for other transitions, yeah, but it's completely random, yeah, for all we know, yeah, and it's not calculable. Yeah, there is no like yet lattice nuclear, yeah, that allows you to calculate it. So you have to measure it from the data.